So I've been working on this mission or some precursor of it for over 20 years now. In 1993, when Alan Stern, who's the PI first asked me if I wanted to help out with this crazy idea of cameras to go on a mission to Pluto. And when I was actually living in Flagstaff in the house that is built on the same basement as one Percival Lowell, not Percival Lowell, but Triton Lowell lived in. And 100 yards from the 24-inch that you were talking about. So I've had Pluto in my head for a long time. Anyway, on with the show. So I can tell you what we know about Pluto, what we don't know about Pluto, and what we're going to find out. That's the idea.
What are you going to find out if you don't know?
Okay, so for those who aren't familiar with where Pluto is, it's way out there. Here we are. I guess we don't. Just the laser pointer. Is there a laser pointer?
Oh, anybody got a laser pointer?
I'll just wave my arms.
Okay.
Oh, the green one's the best. Just everyone has to remind me to give it back. So we're way down near the sun in the middle of this diagram, and the outer planets are pretty spread out. And there's Pluto, the purple one, in this rather crazy orbit that's sometimes close to the sun and Neptune, but right now it's a little bit further away from Neptune. And we now know that Pluto, we thought for a long time Pluto was just out there on its own. We now know there are thousands of objects out here called the Kuiper belt that surround the solar system out beyond the orbit of Neptune. And there's even one other object, there's quite a few big guys, and there's even one that's as big as Pluto, called Eris, but it's so much further away that it wasn't discovered until recently. So Pluto is the king or the co-king or the queen or something of the Kuiper belt. It's not just an oddball out in its own anymore. These are some of its neighbors or siblings to scale. So here's the Earth. Pluto is quite a bit smaller than the Earth. It has this great big moon, Charon. And here's Eris, this other one that's about the same size as Pluto. And a whole bunch of others as well. There's a very rich area with a whole bunch of interesting objects out there. But Pluto is the closest big one. It's the brightest. We know more about it than any of the others, and we know enough that it's going to be an amazing place to visit. One of the things we know about it is that it now has 5 moons. When we launched to Pluto, about the time we launched Pluto, we discovered 2 new moons, and we discovered 2 more after that. We'd already known about Charon, the big one. So it's not just a little object on its own, it's a whole system. And here they all are: Pluto, Charon, Styx, Nix, Kerberos, and Hydra, the names of the new moons there. And there's some very odd things about these moons. What I've shown here actually is one of the odd things that is the number of Charon goes around Pluto every 6 days. Styx takes 3 times as long to go around Pluto, pretty much. Nix takes about 4 times as long to go around Pluto. Kerberos takes about 5 times as long to go around Pluto. And then Hydra takes 6 times as long to go around Pluto. So these moons are all very nicely spaced out in a very regular way. We don't know why. We don't have a good theory for this as to what has put all these moons in these orbits that are almost but not quite in tune with the orbit of Charon. So it's one of the things maybe we'll learn something about when we get there. We think the system was formed by something big running into the original Pluto. You have this rocky, icy object, and some object smashed into it, knocked off a big chunk here that became Charon, and then all this other debris somehow arranged itself into these other moons that are spread out over this very uniform, regular way. Yeah?
Are they coplanar?
They are. They're almost exactly coplanar. Just like it's a little. We're talking about the Jupiter system being a miniature solar system. This is a mini solar system. It's cute. And then, so here's a picture that shows very overexposed Pluto and Charon. There's, let's see, Nix, Hydra, Styx, and Kerberos. We actually know quite a bit about Pluto, what it's made of. I'm not going to show too many squiggly lines here, but this just gives you some idea of the richness of what we can learn about Pluto from the Earth. This is a spectrum of Pluto, showing how much light it emits at different wavelengths, and infrared light a little bit longer than the eye can see. And if it was just made of, I don't know, some uniform plan stuff, you wouldn't see any structure here, but we see all these dips in the spectrum where molecules on the surface are absorbing light at that wavelength. And we see methane, we see carbon dioxide, we see nitrogen. We see the best pictures we have. This is the best picture ever taken of Pluto. It's not very impressive, but it shows you that some areas are very bright, some areas are very dark. So it's got a very rich mixture of chemicals on the surface. It's got some very bright areas, some very dark areas. We don't know what the dark stuff is, but it's some kind of tarry gun thing. It's pretty cold out there, as you'd expect that far from the sun. 38 Kelvin to 55 Kelvin, which is minus 390 to minus 360 Fahrenheit. Pretty darn cold. Then Charon, the big moon. This is not a picture of Charon, but it might look something like this. This is the moon Dione of Saturn, which is about the same size as Charon. It's covered in water ice. There's no water on the surface of Pluto that we've seen, but Charon has a composition of water ice, a lot like Dione. There's dark stuff like there is on Dione. We think there's a little bit of ammonia. But we have these two worlds orbiting each other that are very, very different from each other. We don't know why. Pluto has an atmosphere. It's 20 millionths of the atmospheric pressure here on Earth. But that's still substantial compared to some other places in the solar system. Much, much more than the atmosphere around our moon. We know about the atmosphere because we can watch stars pass behind Pluto. And when a star passes behind an object that has no atmosphere, the starlight just winks out suddenly as it goes behind the object. But for Pluto, the starlight just slowly fades away. So as you're watching the brightness with time, it slowly fades away. There's actually some interesting stuff in the middle, and then it gradually comes back as the star comes out the other side of Pluto. And that tells you there's an atmosphere that is just gradually blocking the light. And so we know a fair amount about it. It's mostly nitrogen. There's some methane and carbon monoxide. And the surface has nitrogen, methane, and carbon dioxide, and the atmosphere has nitrogen, methane, and carbon dioxide. The atmosphere is made by evaporation of the frosts on the surface. And the frosts are continually supplying the atmosphere. They evaporate on the day side, and they condense on the night side. And that actually cools the surface on the day side and warms it on the night side. So the frost is the same temperature of the whole of Pluto at the same time. We're pretty sure about that. It's one of the things we do know. And as the frost moves around, the atmosphere changes. And for some time we were worried that when we got to Pluto, because it's receding from the sun now, that the atmosphere had frozen out on the surface. But we now don't think that's going to happen. This is, let's see, all these points here are measurements of the pressure of Pluto's atmosphere. Here it was the first time we saw it in 1988. We didn't see it for a while. Then in the last few years, Pluto's gone in front of a whole bunch of stars because it's been crossing the Milky Way. So we've been able to measure the atmosphere a whole bunch of times. And it's about twice as dense as it was back in 1998. So even though Pluto is receding from the sun and should be cooling off, the atmosphere is getting thicker. We think it's because of just how the frost is moving around on the surface and how the sun is turning and illuminating different parts of the surface. And there have been models of this, and this is kind of a model that shows Pluto going around the sun and the frost moving around. You see it's on this side, here, and then, well, I should be going this way. And then it starts condensing on the other side. And then evaporates off that side, starts condensing on the other side. So we think there's this very dynamic system with frost evaporating, condensing, winds blowing from one side of Pluto to the other. And we have no idea what Pluto looks like up close, but this is our best guess at the moment. This is Neptune's moon Triton, which is a little bit bigger than Pluto. Has an incredibly complicated looking surface with all kinds of weird stuff we don't understand. It also has a nitrogen atmosphere, methane, carbon monoxide, it's got all that stuff too. But it's orbiting around Neptune. And what we think probably happened is that it formed out in the outer solar system like Pluto did, and then it got captured into orbit around Neptune sometime very early in its history. So it's a long-lost cousin, but because it's orbiting Neptune, we flew by the Voyager spacecraft back in 1989, and we have these beautiful pictures. But we'll have much better pictures of Pluto than when we get there than we have at Triton, because our spacecraft is much more modern, more sophisticated instruments. And you look at Triton close up, and it looks really, really strange. Who knows what's going on? So we've been interested in Pluto for a long time. We've been wanting to send a spacecraft to see what it's like. And the studies went back into the 1980s. But this is Rob Staley here, who was one of the people who did some of the early mission studies for a Pluto mission. Talking to Clyde Tombaugh, who discovered Pluto at Lowell Observatory in 1930, and his wife Patsy. And so Clyde lived, the only person who discovered the planet, who lived long enough, not quite to see it launch, but to see the beginnings of the reality of the mission to actually go to Pluto. He died, I think, in '97. And some of his ashes are actually on the spacecraft on its way out to Pluto, just a little sample of them, which is pretty cool. Yes, and his wife, Patsy, we met her at the launch, and she died just a couple of years ago. So she got to see the spacecraft launch. So there were a lot of talk in the late 80s through the 90s of, oh, we really need to go to Pluto, we've been everywhere else in the solar system. And there were lots of false starts, and for a long time it didn't seem like it was going to happen. But finally in 2001, NASA decided, with quite a bit of public pressure actually, that okay, we'll fund a mission to Pluto, give up bugging us, we'll just do it. And so there was a call for proposals that went out, and because Alan Stern, who I work with on this and who's led the whole effort, had been thinking about this for a long time, he put in a proposal. Here's the cover of our proposal, and here's Alan, who's really made this whole thing possible. And we put in a proposal, and 2 or 3 other groups put in proposals for a mission to Pluto. And we had a site visit at the Applied Physics Lab in Maryland. We were going to build the spacecraft, and we built a cardboard model of it to try and impress the folks from NASA. And we had all these bigwigs and space experts from all over the place came in, and we had a day of them asking lots of questions, giving lots of presentations on what we were going to do. They did the same with all the other proposals, and lots of nitty-gritty. How are you going to solve all these problems that are involved in getting a spacecraft all the way up to Pluto? And then we all bit our fingernails for a couple of months, but we finally got the email from Alan on 29th of November 2001 that he got the call from NASA that we had been selected to build the spacecraft and fly to Pluto, and we've been working on it ever since. So there was a rough design, there was a cardboard model by that point that had been done for the proposal, but turning that into reality is a whole other ballgame, and there was a lot of design work that was done. This was in 2001. We knew we had to launch in 2006, in the beginning of 2006, which means by the time we heard about it, we really had 4 years from when we knew we got the money to actually sending this off to Pluto. And that's a very short period of development for a mission like this. So there's a lot of detailed design and work of all the electrical systems that you need to have, all the instruments that we needed. These are the instruments. There's no point just sending a spacecraft to Pluto, of course. You need to send all these, you need cameras and spectrometers and all these things to actually tell you what it's like when you got to it. The purpose of the spacecraft is just to deliver those instruments to Pluto. So I'll say a little bit about these various instruments. One of the workhorse instruments is called NVIC. It's a multispectral visible imaging camera or something. We just call it NVIC. That will take color pictures of Pluto, a bit like this picture of Triton here, but it will take pictures of 5,000 pixels across. So, which actually for modern digital, cameras, it's not that big a deal. Some people probably have that kind of camera in their phone, but to do it in the dim light out in Pluto, do it very quickly, and to do this with technology that is, well, 10 years old at this point, it was really an impressive camera. It actually has a very, it's not a huge CCD, it's a very long, thin CCD. We sweep it across the sea and we build up the picture that way. That way we don't need to have such a big detector. It's a great camera. But we have a second camera which is called Lorry, and it's only black and white, but this is 4 times the focal length of the MVIC camera, and will take much more detailed close-up pictures in black and white. A bit like this picture of Triton that was taken by Voyager back in 1989. And it's sunk inside the spacecraft here with this aperture here in the door there. This is what I've been working with more than anything else. Then we don't just want to know what Pluto looks like, we want to know what it's made of. And we know that squiggly line that shows all those chemicals on the surface of Pluto. We want to know just where those are on the surface, and we'll learn a great deal from that. And so the LISA instrument, which is over here, is going to measure the infrared spectrum at thousands of points across Pluto, and so we'll say, oh, what's the composition of that crater or this mountain, and how do they relate to each other? We'll get an amazing amount of information from that. And so it makes squiggly lines or colored pictures, but this is just showing a spectrum. I'm not sure if you remember what this is on. So the black points are what you actually measure, and the red points are what you expect to see if you had a surface made of water. And it matches beautifully, almost perfectly. And that tells you without any reasonable doubt, whatever it is, that's the spectrum of it on the camera. It might actually be the moon shower. That it is water ice, and it tells you about the size of the particles and how pure it is and all that good stuff. So that's infrared. We have an ultraviolet spectrometer, which is measuring light shorter than the human eye can see. That's parked up here on the side of the spacecraft. And this will measure the composition of the atmosphere. It will measure the glow of molecules in the upper atmosphere. And we'll watch the sun setting behind Pluto when we fly behind Pluto, and look at the light being filtered through the atmosphere and tell us all about the atmosphere from that. We also have plasma instruments to talk about coronal mass ejections and the solar wind earlier. We'll be measuring the solar wind all the way out to Pluto. In fact, this instrument is called SWRI, it's the Solar Wind at Pluto instrument. The reason we're interested is that Pluto is acting like a giant comet in that its atmosphere is continually leaking out into space. And as it blows away from Pluto, it's going to be displacing the solar wind, and we'll be able to see those perturbations in the solar wind and see how much of Pluto's atmosphere is escaping. And there's a PEPSI instrument which does rather similar things. It's looking at higher energy particles, but they will also be affected by the escape from Pluto. And so we see another dynamic aspect of Pluto from this instrument. And then we have a radio science experiment which doesn't look like an instrument at all, because it's just like the feeder on the antenna up here. But as we fly by Pluto, we'll be sending a signal from the Deep Space Network here on Earth up to the spacecraft that will be passing through Pluto's atmosphere. It's another way of looking at the atmosphere. And we'll be measuring that signal being slowed down by Pluto's atmosphere just before the Earth sets behind Pluto. And so this will give us another way of saying how dense the atmosphere is right down to the surface. And then there's an instrument that was put on later that's called the Student Dust Counter. And it's actually built by students at the University of Colorado who are learning about aerospace. They're aerospace students. They get hands-on experience, not several generations now, of students who were originally building this, but now we've had several students who have been doing their dissertations operating this instrument and analysing the data from it as it goes out through the solar system. And it's like a little microphone, and every time some little dust grain hits it, it goes ping, and we record that, and you can see how much dust there is out in the outer solar system, which we don't know much about. It was fun watching the spacecraft start to take shape. Here is just the basic shell of it in 2004 beginning to come together and start to look at its final shape. You can kind of get a feel here. It's not a very big spacecraft. It would comfortably fit in this space in the room here.
Where is that?
This is at the Applied Physics Lab in Maryland, which is part of Johns Hopkins University. So we're running the mission from Boulder. Some of the scientists are here, and our PI, our principal investigator, is in Boulder. And we're doing a lot of the data analysis here. But the actual hardware is being built, was built in Maryland, and that's where we're going to be for the encounter. We'll all be doing all the operations out there. And here it's beginning to be fleshed out. This is a sort of a mock-up of the plutonium power supply that does power the spacecraft. And I didn't get to watch much of this process. We went out a couple of times, but I remember like standing next to the high gain antenna here that sends the information back, and it's like right next to me, and thinking this thing is going to outlive everything on the Earth. It's going to outlive the Rocky Mountains. It's anything human-made on the Earth is just going to survive for billions of years as it goes out into the universe, which is pretty mind-blowing. So we were on this pretty fast schedule. By late 2005, they were testing the spacecraft, doing spin tests, because it has to be able to spin very evenly, putting in a vacuum chamber to make sure everything works in the properly in the vacuum space and all that stuff. And then in late 2005, it was shipped down to Cape Canaveral. Here, it has all this wonderful golden coating on it, which is insulation. It's mylar insulation that allows you to control the temperature inside, but they had to continually take that on and off to get the stuff inside the spacecraft. So here they're peeling back some of that mylar insulation to adjust something inside the spacecraft. So yeah, it's about the size of a grand piano, and sort of triangular like that. And here it is finished and finally decked out in all its golden coat. And it's being put on top of a solid rocket booster that will take it out of Earth orbit here.
Is that the real plutonium source?
This is not. This is just a markup probably for balance. The plutonium power supply is only put on the spacecraft once it's stacked on top of the rocket at the Cape. It's put in right at the end because it's too hard to work on the spacecraft if you have that close by. You have to be careful of the radiation from it. So it's plugged into the a wall socket or something, I don't know. To supply power until it's almost ready to launch, and then you bring in the plutonium power supply, you plug that in, you switch it to that power, and then that's what's going to sustain it for the rest of its life. Here it is being put inside the rocket fairing. And this is like the last time anyone actually saw it, at least out in the open. Alan Stern, who I think it was a little hard to get him away from his baby, inside the fairing until the very last minute when they had to kick him out. And then here it is, all sealed up in the fairing, being taken out to the launch pad, and it's be lifted up on top of the Atlas rocket. The rocket was built down Lockhart in southern Denver. There it goes up on a crane to get on top of the rocket. And there it is, launched in January 2006. Launched, it was a couple of days delayed, but it really went very smoothly. It's a really tiny spacecraft on a really big rocket. The result being it goes really fast. And it's the fastest ever launch from the Earth. It took 9 hours to get past the moon. It sure looked, I haven't seen any other launches, so I don't have much to compare it to, but it sure went off fast, and as far as I can tell. Here it is heading for Pluto. Here we are, being very happy to watch it. And that was quite a day. And then we had the party afterwards. We actually had a series of parties afterwards because you get the caterers or get all the food arranged, and then the launch is scrubbed and you've got all the food anyways. We had a couple of false starts to the launch rockets, but then finally we got the launch team all got replica rockets and pictures and things. And my favourite bit was the burning of the contingency plans. I guess it's a ritual for space launches. You have to, all the things you would do if something went wrong that you don't need once it actually launches. But now it's probably not paper, you just delete a file on the hard drive. It's not the same. So we're going so fast, it took us only 11 months to get to Jupiter. And Jupiter's our only stop, well, it wasn't a stop, it's the only place we passed on the way to Pluto. And so it was our one chance to fly by a planetary object and take pictures and try out all our instruments and make sure we knew how to command the spacecraft. Here's our trajectory. We didn't come really close to Jupiter. It wasn't our kind of objective. I think we were like the 9th spacecraft to Jupiter or something. Jupiter's old hat. But we needed it to give us a boost to get to Pluto. But we were obviously interested in looking at Jupiter when we went past. So here we are out beyond the orbit of Callisto. Someone was mentioning Callisto earlier. Quite a ways out, but still getting some significant gravitational boost from Jupiter. You notice when we went past, all the moons were hiding on the other side of Jupiter. So we didn't get as close a look at the moons as we would have liked to. But again, that wasn't our prime objective. We did get lots of nice data. This is our infrared spectrometer that takes infrared pictures and spectra of Jupiter. In this case, got these beautiful, make Jupiter any color you like. With we had 200 wavelengths of light, each of which is telling you something different about the composition of Jupiter's atmosphere. Yeah, we could see ammonia thunderstorms in Jupiter's clouds. That's on the next picture, in fact. There you go, ammonia thunderstorms in Jupiter's clouds. Which you can tell just by the particular wavelengths of light that they absorb. And we could do it several times so we could see the development of these things. No one had been able to do that before. And here's a color infrared picture of Jupiter. It doesn't look like, you're used to Jupiter looking like this is a great red spot, not looking very red, just because we're not looking in the visible light that we normally look at. This is a view from our NVIC, our big color camera, which did not take color pictures of Jupiter because it's too bright at Jupiter. We designed our cameras to work at Pluto 30 times further from the Sun than the Earth, where the illumination is 1,000 times dimmer than it is at the Earth. And with Jupiter only being 5 times further from the Sun than we are, everything was so brilliantly illuminated by the Sun that our pictures were overexposed. And we could only do a few special things that allowed us to take pictures that were not overexposed with our visible camera. So this is in methane light. Methane in Jupiter's atmosphere absorbs a lot of the light, so we could get a picture, but we can blow that up to give you an idea of the kind of detail that we're seeing in this picture. And our pictures of Pluto will be even better than that. One of my favorite moons is Io, and the volcanically active moon of Jupiter. We took a lot of pictures of Io. Some pretty amazing pictures, actually. There's this huge volcanic eruption going off near the North Pole called Flagstaff. What this picture shows is this is the glow of the red-hot lava at the heart of that volcano. And then there's this huge cloud of debris being blasted into space from that volcano. Part of it's on the night side, it's actually being lit up by Jupiter. But this is lit up, it's rising into sunlight even though the volcano's on the night side, and you see the shadow of Io cutting across that. It would be an amazing thing to be on the surface to see that. Here's our color camera. You can see the picture's not quite as detailed, but now we can see that red glow and that blue smoky, very fine smoky particles in that plume. And then this is the base of the infrared instrument that is showing the heat radiation from all the volcanoes. So each of these is an active volcano, and this is the biggest and brightest of them, which is the Flagstaff volcano there. So you have all these different ways of looking at Io with our instruments and seeing different things. So a whole bunch of volcanic plumes. These are all volcanoes blasting stuff into space. Here you actually see the surface of Io lit up by light reflected off the plume down onto the surface. And then the glow of the volcano in the center, all kinds of fun stuff. Io glows in the dark. This is when Io's in Jupiter's shadow. It will be completely invisible if you're looking in ordinary light. Well, actually, I'm sorry, this is ordinary light, but it's very long exposure, so we see these very faint glows from volcanoes here, and then the atmosphere of Io is glowing. We don't even know what's going on over here. And sort of by dumb luck, we actually were able to get a movie of this eruption, and you can see this fountain, this 300-plus high fountain of debris falling back down onto the surface from that volcano.
What about the area of the US or half the US?
Well, it's about the size of Texas, maybe the fallout region from that volcano, something like that. Io's about the size of our moon, it's about a quarter the size of the Earth. One of our parting shots, Io passing Europa. We actually put out on the internet for suggestions as to when to take pictures, and someone said, oh, it would be really cool to take Io and Europa passing each other at this particular time, so we did it, and it was. Here's another picture of Europa rising above the cloud tops of Jupiter. Nice pictures of the ring. Some of the most detailed pictures of the ring that we've ever seen. Jupiter has a very thin ring, not like the huge rings of Saturn. And then we were just off into the void. And 3 years after launch, we had a cake. 6 years after launch, we had a cake. We had a cake every year, actually. I'm not going to bore you with all of them. But we weren't just sitting twiddling our thumbs in this long cruise out through the outer solar system, of course. We had a lot of work to do to plan exactly what we were going to do when we got to Pluto. And
You're going to have a cake.
We'll be too busy to eat. Here's our trajectory, actually. In fact, this is on the New Horizons website. I should have put the address. You can just Google New Horizons, you'll find it. Is a live view of where we are right now. So I downloaded this morning. It's not a complicated trajectory. It's sort of bat out of hell trajectory. You see we trajectory changed a little bit as we passed Jupiter back here, back in 2007, and then it's pretty much a straight line all the way out to Pluto. And you can see how close we are now. Only a year to go. It's getting exciting. So all through this time, we've been planning is my good friend Leslie Young, who's leading the planning process, doing some math with a ruler on the board. We cannot control the spacecraft in real time. It's 4 light hours away to Pluto. It's 4 light hours back before we can learn anything from the spacecraft. So the whole sequence of what it does at Pluto has to be completely pre-designed. And we have spent years haggling over every little piece of that plan. What pictures we're going to take when, how to deal with anything that might go wrong if the spacecraft computer crashes in the middle of a sequence. Normally if a spacecraft computer crashes, the spacecraft does the safe thing and it stops doing whatever it's doing and radios back home for instructions. We can't let it do that. Because by the time it's radioed home for instructions, it's not slowing down. Pluto's going to be long gone. So it has to be able to pick itself up, get back on the sequence, keep executing its commands, even if the computer crashes. Not that we expect the computer to crash, but we've got all these contingencies that we're having to deal with. If we lose one observation with one camera, well, we'll try and take the same observation with another camera later. So if one of the cameras fails, we can still get that science from another observation with another camera. And of course, we have to do everything very fast and very efficiently. We're flying by 14 kilometers a second. Essentially, we're done with the whole encounter in 4 or 5 hours. We have no chance to do it again if we get it wrong. So lots of poring over laptops and debating pros and cons and this, that, and the other. But here's our plan. But this is a small part of our plan. And obviously there's too much information here to go through, but here is Pluto. There's Charon, which will be on the opposite side of Pluto from where we fly by. And here's our trajectory through the system. This is Pluto's shadow. This is Charon's shadow. We actually fly through those shadows after we pass by Pluto. So as I said, we can watch the sun setting behind Pluto and learn about the atmosphere. Each of these bars here is when we're doing one particular observation. So, for instance, okay, out here is our full mosaic of the whole disk of Pluto. Here is a close-up view of part of Pluto. These are the red times when we're doing composition scans with our infrared instruments. We have a whole bunch of stuff we're doing at closest approach with the highest resolution, the sharpest, most detailed scans, and so on all the way through.
How much data are you storing? I assume you have no chance to get it back.
Right. It's going to be different from some other missions. Like the Voyager missions were able to take data and send it back simultaneously because they always pointed their main antenna at the Earth, and then they had a camera that could point in different directions, so they take pictures, send them back, take pictures, send them back. We can't do this, our antenna is fixed. If we're pointing at Pluto to take pictures, the antenna is not pointing at the Earth, so we can't send anything back. And our antenna is a small spacecraft with relatively low power, so we just can't send stuff back at the same rate. But unlike the 1980s when Voyager was flying past the outer planets with its 8-track reel-to-reel tape recorder, we have gigabytes of solid-state memory. And I think we have like 64 gigabits or something of redundant on the spacecraft. So we take gigabits of data, and then we take about a year to send it all back. Yeah?
What is the rotational axis of Pluto and Charon with respect to the Sun?
It's sort of tilted 45 degrees by the time we get there. So the Sun is shining 45 degrees off the equator on either the northern or the southern hemisphere. One of the things that's very confusing about Pluto is they keep changing the definitions of the coordinates. We're not sure. For years we thought we were going to be approaching the southern hemisphere of Pluto. And then the International Astronomical Union changed its mind, and now we're apparently approaching the northern hemisphere, but I just found out today we're not supposed to call it the northern hemisphere, it's the positive hemisphere. But anyway, so we think we know where we are, we just don't know what to call it.
Is the direction of rotation more or less like the Earth-Moon system?
No, it's...
And the Jovian system?
The reason it's confusing is it's tilted on its side. Which is why it's hard to say which is the northern and southern hemisphere. It's actually tilted a little bit past on its side, like Uranus is. So it's rotating backwards if you want.
Close to the 90 degree rather than...
Yeah. Okay. But the angle that we're coming at it is about 45 degrees of the equator. Yeah.
Is that orientation pretty common for TNOs?
I think most TNOs are, well, we don't know the orientation of many TNOs, so that's Kuiper belt objects. These objects are on Neptune. We don't know the orientations of many of their poles. People are actually looking, quite a lot of them are binaries, have two TNOs orbiting each other, and we've been looking at the angles at which those orbits are, because I think that tells you something about how they form. And so I don't think it's quite random, but they're all over the place. But we suspect Pluto got tilted at this angle by the impact that created the Charon and all the other moons.
Are they tidally locked?
Charon is tidally locked. It's a unique system that, of course, our moon is synchronously orbiting the Earth and always has the same face to the Earth. But the Earth is just spinning independently of the moon. In Pluto and Charon system, Charon is so big compared to Pluto and they're so close together that they're both completely locked to each other. It's a rigid system. You could build a bridge from one to the other. We don't have the budget. Sorry?
The very center of Avogadro.
Oh, yeah. And they're actually both orbiting about the center of mass, which is outside Pluto. So Pluto is doing this little tight orbit around the center of mass, and Charon is doing this much wider orbit around the center of mass. But the other moons, we're actually very puzzled about their rotation. All we can say is how their brightness varies. And it seems to be varying in crazy ways. We suspect the other moons are chaotically rotating, because instead of orbiting a single planet, we're orbiting this crazy dumbbell double planet thing. And that makes the gravity weird enough that they just can't settle down into synchronous rotation. We have some evidence for that, but we really are going to want to figure that out when we get there. So we have a whole series of milestones on the approach. The first one we already passed. This is a picture we took last summer. The spacecraft is mostly in hibernation, but once a year we wake it up for an annual checkout. And the last annual checkout last summer, we took our first picture of Pluto. There's Charon. We can now see it separate from Pluto. And that's pretty exciting. It's no longer just a dot, just a pixel. We're starting to see detail in the system. It's not as good as the best pictures you can get from the Earth or from Hubble, but it's showing we're getting close, and that was exciting. This summer we'll do it again, but now we're much closer and they're brighter, and this is a simulation of the kind of pictures we should get this summer, and they'll be really clearly separated. We won't see the other little moons yet, but we'll start to see those in January 2015, which used to be a long time ago, but it's now next January. Then we will be getting into full-time observations. We'll come out of hibernation, we'll be taking observations every few days, and then we'll start to see the little moons as well. There's some debate about this, but I'm claiming by early June 2015 we'll get the pictures of Pluto that are better than these Hubble pictures. So we'll have about 6 weeks, 8 weeks also of constantly getting better pictures. One thing we'll be doing on approach, that I'm spending a lot of time on at the moment, is we keep finding new moons. The harder we look, the more moons we find. We've got to fly through this system. And if it's just completely full of debris, not the moons themselves, but any dust and stuff that might come off those moons, that could be a danger to the spacecraft. So as we're approaching, we'll be continually taking pictures with more and more detail to try and find those additional moons or rings or anything that might be dangerous to us. This is a simulation. We're running a simulation at the moment that I did showing all kinds of imaginary moons orbiting Pluto here. That we're making imaginary pictures of them. I'm putting moons in these pictures, sending them off to the team who have to try and find them. And I'm cheating here. They're not nearly as easy to find as they look here. And they're going to see if they can find this, so we're ready when we get there to quickly analyze the pictures when they come back. If there are moons, we'll know where they are, we know what they're doing, we'll know if they pose a danger or not. And we have to do all this very quickly when we get there, so we're practicing. We don't think there's a danger, and this is why. This is a computer simulation, and it's kind of now we're looking at, here's Pluto's equator, and the moons are all along here. And the way I've drawn this, we kind of come through this sweeping arc past Pluto. Pluto's out here. And in this is a computer simulation where we completely fill the system with junk. That you would never fly through the Pluto system if it looked like this, but there's just crud everywhere. And then we calculate the orbits of each of those particles for a few hundred years. This is what it looks like after just 500 years. What's happened is Pluto's in the middle, and Charon is just sweeping through here, this big moon, and every 6 days it's just clearing everything out of that region. That stuff is being colliding with Charon or being thrown out of the system, and it makes this wonderful gap for us to fly through. And so we're pretty sure that there's nothing can survive Charon's gravity in the region where we're going to go through the system. But we're going to be sure about that, and we're going to be checking on approach. But I'll be very surprised if we see something. This is our view about 3 days out on July the 11th next year. This is going to be interesting. Oh, these are simulations assumed if Pluto was the moon, our moon. Just to show the kind of level of detail we will see. I'm sure there's nothing like this. But this is the best view we'll get of the opposite side of Pluto, the far side. It's a 6-day rotation, so 3 days out we'll get our best view of the opposite side, and then that will rotate away and we'll get a much closer views of the opposite hemisphere. But if you know the moon well, there's the Tsiolkovsky crater, so you can still see quite a lot of detail, even 3 days out with our telephoto camera. This is 1 day out, and if there were craters on Pluto, I'm kind of hoping there won't be, I'm hoping there are more interesting things. We'd see a lot of craters and a lot of detail by that time. The last image we will send down before we get to Pluto will be about this big. And this will come down, not that we're counting, but at 11 p.m. Eastern Time on July the 13th. And we'll get that one picture on encounter day. And it's going to be interesting. We'll have 50 scientists trying to analyze one picture. And we'll all get our own pixels, I guess. So should the worst thing happen and we collide with something when we actually reach Pluto, this will be the best picture we ever get. But that's not going to happen. Then this is now 12 hours out. We'll get this kind of level of detail. This shows the view of the pole, whichever pole it is on approach. So you see we're tilted about 45 degrees. We have a good view of this hemisphere. We don't get a very good view of the opposite hemisphere. Then I think about 5 hours out. We're now mosaicing. We can't fit it all in one picture. So this is a series of 4 by 5 pictures that will cover the disk of Pluto. This is, I think, about 2 hours out. Now, each picture is just showing a little tiny piece of Pluto, and we're taking this mosaic. We don't even have time to cover the whole of Pluto at this level of detail. But that big chunk of real estate will cover in this beautiful detail. Each of these is a 1,000 pixel image. About the same time, we'll be doing our maps of the composition, and we'll make, this is Mercury, but we'll be making color images showing all the different frost, different kinds of frost on the surface, and learning where they are and how they interact with different kind of geology there. And then our best global pictures, which are taken about 40 minutes before closest approach. You have to imagine the whole moon at this kind of level of detail is the kind of quality of pictures we'll get there. So this is going to be exquisite. Here's one of our, this is the blue rectangle is a scan with our color camera, and then each of these is each square is a single telephoto view of 1,000 pixel, 5,000 pixel telephoto pictures spanning the entire disk. And who knows what's going to be in those pictures, but it's going to be amazing.
What's the yellow black line?
Oh, this is the terminator. So this is the day side, this is the night side. That's the line between. Yeah.
Are you going to get both Pluto and Charon pictures?
Oh yeah. We'll take more pictures of Pluto. It's closer to us. It's bigger. It's probably more interesting. But we'll get lots of good stuff on Charon as well. And even the little moons too. We'll turn and look at those. Nix, the little moon Nix, we're going to look at the most. And then we won't get very good pictures of the others, but we'll take a quick look at them. This is our closest view of all. This is right at closest approach. Even with our wide-angle color camera, we can't fit the whole of Pluto in, but we'll sweep across it like this with another very narrow noodle of very high-resolution pictures down the middle. See stuff down to about 100 meters across. And this is one of our planning sequences. You may wonder why there are 3 Plutos here. The reason is we don't actually know where Pluto is. We can look in the sky and we can see with very high precision where it is in the sky, but knowing exactly how far away it is when it's 4 billion miles away or whatever it is, and it's only 1,000 miles across. Knowing its position in the direction of the plane of the sky, or against the plane of the sky, to sufficient precision to target precisely on it, we just don't know it that well. So we have to say it might be over here, it might be here, it might be here. Wherever it is, we're going to take pictures of that whole region. And that's how we'll catch it wherever it actually turns out to be. And so here you see, here's our high resolution camera again, sweeping across all these Plutos, one of which will be real. And someone was asking about Charon, this is in movie 2. Yeah. Here is actually coming out, Charon coming out from behind Pluto. Charon could be anywhere in this region, but here again is our camera sweeping across there, taking high-resolution pictures of wherever it is. So we have to take pictures all the way from here to here, just to be sure that Charon will be in there somewhere. Here's kind of a view of our best pictures of, we don't know how big Nix is. It's the little moon that we get closest to, but if it's on the large side, then it's going to fill most of the camera frame. So that's going to be very interesting. We've no idea what these moons look like. We know very little about them so far. And then we pass behind Pluto. We watch the sunset in Pluto's atmosphere. The light passing through the atmosphere, we analyze with our ultraviolet instrument, learn all about the composition of the atmosphere. And then we do it again at Charon a couple of hours after that. And after that, we turn and we look back at the crescent, which might look something like this. This is the crescent of Triton, seen by the Voyager spacecraft that departed in 1989. And you can see the fuzzy edge with the thin atmosphere there, and all kinds of exotic things. There are plumes, sort of like plumes of smoke coming off the surface of Triton. We don't know what they are, because our pictures are not very good, but they're very intriguing, showing that the surface is active. We may well see something similar on Pluto. So here's one of our first views back, and again, each of these squares is one of our high-resolution cameras that will be going all the way along that very thin sliver of crescent. I think these are going to be beautiful images. And then we'll be looking, I said we only see one pole in approach. We don't really see the winter pole, but what we're going to try and do is look in Charon light. So Charon is going to be over here, illuminating the night side of Pluto, but very, very feebly. And we're taking very long exposure pictures. They'll be blurry, they'll be horrible, but we're hoping to see some illumination of that dark side, and see something about is there a North Pole or South Pole cap on that side of Pluto. And then we keep going. We're not going to stop. We go out into the Kuiper belt.
And you're traveling how fast at this point?
14 kilometers a second, more or less.
How does that compare to escape velocity from the solar system at that point?
It's a lot more. So we're beyond escape velocity from the solar system. We're just going to keep going forever. I don't think we slow down much more. By the time we're completely out of the solar system, maybe we're going 10 or 12 kilometers a second. I don't actually remember the number. But way over escape speed, which is why we're going in this nice straight line. So here's the Pluto encounter, and then the Kuiper belt, all these hundreds of thousands of objects out beyond Pluto. We want to look at those as well if we can, or at least some of them. And this is proving to be challenging. We know of about 1,000 or 1,500 Kuiper belt objects now, but the survey is completely very incomplete, and we only know where most of the big ones are. And we can only change our trajectory by a very small amount because we're going so fast. So we really can only look for objects we can only fly by objects that are right along this line or very close to it. And we don't know of any objects that are there. And from the statistics, they ought to be out there, just because there are so many Kuiper belt objects. But we have to find them for ourselves. And so I've been in charge of that process for the last few years, and yeah.
And is the mass estimates of the Charon system, are those nailed down well enough to where you've got a pretty solid line there, or do you have to put your bar on the side?
No, we know where we're going pretty accurately. We know the mass of the system very well because of all these moons that allow, from the timing of the orbits of the moons, you can measure the mass of the system very well. Our Pluto's mass is so small and we're going so fast, it diverges hardly at all. It's not like flying past Saturn or Jupiter. Yeah?
Will the battery last as long as Voyager's?
It's the plutonium power supply is what limits the lifetime. I don't think it will last as long as Voyager's. We only have one, they have 3. And they're still going. You know, Voyager's launched in 1977, but we're still in communication with them. They're at 120 astronomical units now. Pluto's only at 30 astronomical units. And the Voyagers, I think, will have contact with them for another decade or maybe a bit less. I don't think we have as much power as they have, and I don't think we'll be able to be in contact for quite that long. But we haven't done that study to really figure that out right, exactly how all the ways you can save power to continue to communicate is going to be a job for the future. But we probably till at least 2030 at the while, I guess.
How long is the project?
Only till about 2016, which means we have to apply to NASA for continued funding for an extended mission, which partly depends on finding a Kuiper belt object beyond Pluto, because if we've got one of those, then we have a very strong extended mission. So the wee problem with this is the place where we have to look is right in Sagittarius. look, these things are very faint, they're 26th magnitude or so. And that if you're in a dark sky, that's hard enough, but when you're looking against the Sagittarius star clouds for something of 26th magnitude, it's really hard. I wish I could tell you we had found something yet, but we haven't, we're still looking. But here we are, 2014, we're moving out of Sagittarius now, the star density is dropping to where I think we'll have better luck this year. We're using the SWRI telescope on Mauna Kea, that's one of our prime telescopes, and then the Magellan telescopes down in Chile. And these have wide field cameras, they're very big telescopes, so it's 8 meter and 6.5 meter telescopes. And so we found a whole bunch of KBOs. We found, well, here's one of them, it gives you an idea of how hard the task is. We take images, and there's all these stars in the images because we're looking at the Milky Way. And you take images at different times and you subtract them to try and get rid of the stars. But because the seeing is never constant, the stars are varying, but mostly it's just the seeing is always changing. You cannot perfectly subtract the stars, and so you go from this to kind of this kind of crowd, and there's KBO. So look here, it helpfully has a circle around it. It didn't before we found it. And so it's a huge job. We've sifted through terabytes of data at this point. We found about 50 of them, but none of them are quite where we need them to be. The closest one, if we had 60% more fuel in the tank, we could get to it. It's frustrating, it's that close, but we just can't get to it. So we're continuing to look to find ones that are closer to our trajectory. This one was magnitude 25.7, it's one of the brighter ones.
Any chance to use a Hubble and do a deep field cycle?
Well.
When is it?
There's a long story.
That's fine.
I was almost submitted a proposal to Hubble today for 150 orbits of Hubble time. Hubble could do this pretty well, but it only has a narrow field camera. It can see very deep, but only with a narrow field, so you have to spend a lot of time just searching the whole region with all these images, and that makes it very expensive for Hubble time. And we have yet to persuade them to do this.
Is there a way to look down the line of trajectory?
Yeah, it's not exactly there because everything's moving, you have to correct all that, but we know where we need to look. But it takes a little bit. And then the spacecraft itself cannot do this. Its cameras are not powerful enough, because the camera has a lens this big on it. And we don't have the data rate anyway to send out all the images we need. So it has to be done from the Hubble or from the ground. So we're still working that problem, but we're still working from the ground. This is our new trick up our sleeve. We've been using a camera called SWRI cam on the SWRI telescope, which is, I guess it's a pun, it's the prime focus of the telescope. So you've got the telescope, the primary mirror down here. The camera just sits up at the main focus here, and it has a huge field of view, about half a square degree, so you can fit the entire moon, half a degree square, so you can fit the entire moon in the field, which for that size telescope is huge. But now we have hypersynchronous prime cam, which is, well, this is the size of the camera. It's bigger than most telescopes. Yeah. Just the camera itself, the lenses are made by Canon, I think.
And that's a child's doll standing beside it.
Yeah, you can tell it's a Japanese project. And the nice thing about this is this summer, this is where we think any kind of capable object that we can reach is going to be here in the sky. This is our field of view. So we can catch them all at once. If they're out there, we will catch them. We just have to go deep enough. We're looking forward to using this for the first time. Maybe this will find us out KBO. But if we're lucky, and everything, we do find one, we can target it next year. Sometime around 2019, I can come back and tell you about pictures like this, which will be probably the only pictures we'll get in the lifetimes of all but the youngest of us here, of any object out there, of these hundreds of thousands of objects out in the solar system, and the composition and everything else we can learn about them. So hopefully we've got that to look forward to, but in any case we have a fabulous, exciting year next year with everything we're doing. That's it, thanks.
Yeah, I was just gonna say you had those error ellipses around the position of Pluto. Are you gonna be able to refine those over the next time frame?
What we're doing is we're approaching Pluto pretty much in a straight line.
Yeah.
Which doesn't tell us it's, you know, it's the same view. We know where it is in the sky, we can't tell how far away it is, it's a precision read. Just the last few days, we start to get a bit of an angle on it, because we're not flying straight at it. So the last few days, there's a lot of scrambling. Once we start getting that angle, getting the pictures down, we're not changing the trajectory or anything at that point, but we're telling the spacecraft, okay, this is where Pluto is. So it will know where to point at it. And all the instructions on the spacecraft say, don't point at this right ascension declination. They say, calculate where Pluto is and point there. So we can change those within the last couple of days. But it's all going to be this very kind of crazy, hectic end game doing all that. But to make those errors as small as possible, we're doing all the tracking we can do. In fact, we've gone back to at Lowell Observatory in the 1930s and 40s. They kept tracking Pluto after its discovery. And they have all these photographic plates down in the basement. And they tell you the position of Pluto at a time when nobody else was really looking very closely. So we've been able to analyze those plates just this past year, and they tell us the orbit more precisely and will allow us to get its distance better. So we're narrowing it down as best we can from the Earth as well. But yeah, that's been the whole thing. We're also using the ALMA array and the Atacama large millimeter array, which should be a whole different way of measuring the position of Pluto very precisely.
Yeah, what type of record of human history is on the spacecraft? You know, the Pioneer had the plaque and the Voyager had the disc.
Yeah.
Well,
we don't have anything like that. We have partly because the spacecraft was done in a hurry. We didn't have a lot of time. The main thing is to get the spacecraft ready to go. There's bits of Tombeau. There's a Florida quarter. There's signatures from signatures and pictures of the team, but it's on a regular CD that's going to decay in a few hundred years, so there's no chance of immortality. Then there's, of course, the spacecraft itself, which is going to tell you a great deal about the people who built it. But we don't have a deliberate self-conscious record of humanity the way the Voyager does this kind of machine.
Going to come back.
Compared to the Cassini trajectory, this is a rifle shot. Any comments on why you chose to go so fast? Was that just the rocket vehicle, or was it to get there while you were still,
We wanted to get there before we died. Some of it comes down to just the expense. That the longer the mission, the more it costs to fly. And some of it comes down to reliability. It's a lot harder to build a spacecraft that you know will last for 20 years than one that you know will last for 10 years. There's just a whole other level of, it can be done. The Cassini spacecraft has been going that long, the Voyager spacecraft. But part of that is luck as well. If you absolutely have to guarantee the spacecraft lasting that long, that's a great deal of additional expense in the kind of testing and the components you have to use to do that.
And so really the only way to run the mission is to get there fast.
Right, and besides it works. We can take data extremely fast with modern instruments. If we were going half the speed, it would be nice, but we'll probably get 80% as good data going at the speed we are. Just because the spacecraft can turn so fast, it can store data so fast, we can make very good use of that time.
You say it's going to take a year to get the data back?
Well, as I say, we get this best picture back before encounter, and after that, over the next week or two, we've prioritized which pictures will get snippets of good stuff. It will all be compressed though, it'll be JPEG compression or something like that, and the pictures will look great from a distance, and when you look up close, they'll look a little cruddy because we had to compress them to get them down in that length of time. And then we actually have a period of a few weeks, which is going to be frustrating, where we won't be doing very much because we have a small crew and we have to plan the sequences as they come up, and we don't know when we're going to get time on the Deep Space Network until fairly short time in advance. So there's a period of a few weeks after the encounter which we would have to be planning just as we were approaching Pluto. And we just don't have the manpower to both deal with approaching Pluto and figure out where it is and so on, and do all this planning of this sequence. So we're going to stand down, just do fairly minimal stuff for a few weeks, and then we will send back all the data compressed over a couple months. So by October or so next year, we should have everything down with these blocky, JPEG-y kind of images and all the other data. And that will tell us where the good stuff is. And that will give us some priorities to when we then send down the real data. But then we want to send every pristine bit back without compression, without cutting out the dark sky, because you lose what might be in the dark sky. We'll be doing some of that early on. Just like Pluto's in a big black background, we just send back the bit that has Pluto in it. But we'll send back everything, and that will take about a year.
What kind of data rate
I don't remember the number. Is it 12,000 bits per second or 10,000 or something? But I could be wrong.
This Voyager is really slow.
We're a lot slower than Voyager. We're a much smaller spacecraft, and we don't have the power of Voyager. And we don't have a big Voyager.
We had very little power, like 16 watts or something.
Oh, we got less than that. I don't remember. Yeah.
Do you know anything about the laser communications that was tested on Lady? How would that affect downwind rates for future outer solar system missions?
Oh, you know, people have been talking about that for decades, and there's a lot of infrastructure developed for it, and the current techniques work well enough, and so there hasn't been enough incentive, I think, to really invest what's necessary. I mean, it's not simple. If you're sending it back down by a laser and it's cloudy, you got the same problem as you guys have here. You'd really, ideally you want some kind of space telescope, use Hubble or something to intercept data, and that's very expensive. So it's not a simple situation. Yeah.
What's the diameter of your telescope? I guess it was Lori, was it?
Lori is the telephoto one. It's about this big.
3 inches or something.
It's a reflecting telescope, and yeah, it's 8 inches. Sounds about right. It's pretty good telescope. It's got 1 arcsecond pixels.
Semester?
Yeah.
Did it take very long to figure out all the cute acronyms?
Yeah, well, it's a NASA mission. You've got to have the acronyms, but not actually. Our infrared package is called Ralph, and our ultraviolet package is called Alice, and I think they're named after the honeymooners.
If you find more than one object in your trajectory, can you do more than one flyby?
We could, but they'd have to be lined up right. I think at this point, early on, we had hopes that we'd be able to do that, and we could still get lucky, but it's more likely we'll find one over here and one over here, and we'll have to choose between them. Partly because they're all kind of at the same distance. They're all going to be around 45 astronomical units. That's where the densest part of the Kuiper belt is. And so they won't be strung out along our trajectory, they'll be all kind of bunched up, and that will make it harder. But we could get lucky, and we still will be open to that possibility.
Well, how do you choose them?
If we had to choose,
But you can't hit them.
it might be the right. Well, we'll get Hubble on the case, and we'll see, for instance, if one of them is a binary, we'll go for that one. A lot of them are binaries out there.
Why binary?
Well, you get 2 objects for the price of 1, and the binaries are very interesting. They're telling you a lot. We don't quite know how binaries form, but they're very common in the Kuiper belt. A lot more common than they are in the asteroid belt.
And you can figure out the mass.
You can figure out the mass. But also, the way they form has a lot to do with the collisions in the early history of the Kuiper belt. They're very interesting in that respect. So I think we'd go for that. Otherwise, we might just choose the brightest one, or if they're different colors, we might choose the one that's the most interesting color. We'll see.
Are there any missions after New Horizons? Like, what's on the drawing board now? What do we get to see in the next 10 or 15 years?
Well, it's a little scary. It's kind of drying up. There are, what is it? There's the asteroid sample return mission that is going to be going to an asteroid, landing and bringing it back out. Or not landing, it's actually going to hover and scoop up a piece and bring it back. There's Juno, which is already flying. It's on its way out to Jupiter. It's going to go around Jupiter in 2016, I think. But it's already, it was started 10 years ago. It's been flying for 4 or 5 years. There's a Mars landing mission. I'm spacing out on the names now. Somebody in the audience probably knows that we'll be landing a seismometer and running around the interior of Mars.
Well, I'm saying missions past Pluto.
Exactly.
Missions past Pluto. This is a new horizon. What's beyond that?
Yeah, we have nothing else going to the outer solar system. We're hoping to get a Europa mission, and the Europeans, of course, are planning a Europa mission. I was on a telegraph about that this morning. It will get to Europe in 2030, or get to, sorry, it's a Ganymede mission. It will be flying past Europa, but it will be orbiting Ganymede, and it will get there in the early 2030s. And the Americans, NASA wants to send a mission to Europe, has been planning it for 15 years or so, but has never quite got the funding together. And there's a streamlined version of that now called the Europa Clipper that might be sent out. Well, it might get funding in the next couple of years, but it's not really. There's no guaranteed funding for that either. We have Mars sample return on the horizon. The Europeans going to Mercury. Quite a lot of the work now is being done by other countries. It takes a long time to get good at this, but now the Europeans and the Japanese and the Chinese are getting kind of good at this. So they'll be picking up some of the slack.
How much should this cost?
About, depends what year dollars you use. In current year dollars, I think about 700 million, which for an outer solar system mission is pretty cheap. Cassini in current year dollars $4.5 billion. So we're a much smaller, lighter, cheaper, more streamlined spacecraft than Cassini.
Given that time here, we've got donuts and coffee waiting for us. Are you going to join us over at the observatory?
Maybe briefly, yeah.
Okay. Let's go for one more question. If there is one, if not, we can plan on.
Well, I can show them the movie.
Oh, yeah.
This is just, I think it's fun. This is, as I say, we've been simulating what we'll see on approach so we can practice looking for moons and things. So this is, we're disconnected. That's all right. It's a cute movie, simulated showing Pluto and Charon orbiting each other and getting brighter as we approach.
Looks good on the
Anyway, we've run out. So.